So today we are going to start lecture 8, and this lecture is going to be on the golden section search. Now we have seen in the previous lecture that the equal interval search method, it essentially keeps taking steps of the same size, and after a certain point it is going to bracket the minimum point. Now you can intuitively see that it would be better if we took progressively larger steps till the minimum was bracketed, and then once the minimum has been bracketed we could again refine this particular interval by taking smaller steps. So these kind of methods are known as variable interval search methods, and one of the most important such methods is the golden section search, which we are going to discuss in today's lecture. Now here the step size keep going up as you move rightward on the graph, and the minimum point is going to be bracketed in a manner which is much faster than using the classical methods. Now the golden section search is based on a certain number known as the golden ratio, and this number is defined as 1.618, and we will see how this comes across. So this is a truncated version of this number to 3 decimal places, because this golden ratio is not a rational number. And we will also see that instead of taking a constant value of delta, we use a value r delta, and this r keeps changing based on the location you are at in your search. Now, one of the reasons for the fame of golden ratio is that it is used in many particular situations and comes across in geometry in many situations, and it is supposed to have a pleasing disposition. And therefore, for example, in Greece, a rectangle with sides of the ratio 1:1.618 was considered to be a very pleasing rectangle, and this was known as the golden rectangle. So again, just keep in mind that this number 1.618, which we will use in the algorithm today, is known as the golden ratio. Now we will look at how we can get this particular golden ratio. The golden ratio comes across in many places in the branch of mathematics known as number theory. It's also sometimes known as the divine proportion and the golden mean, and it is often encountered when taking the ratio in geometric figures. So let's go back to the definition propounded by Euclid long ago, which is referring to a line segment. So let's consider the line segment AB. Now in this AB, this length AC is given by tau, the Greek letter, and the length CB is given by 1. So with this particular definition that there is a line segment AB, AC is tau and CB is 1, let's find this point C between A and B such that tau is AC by CB, and you can see it from this line segment here that tau would be AC, which is tau, divided by CB, which is 1, so tau by 1. And this is also equal to AB by AC, because AB would be tau plus 1 and AC would be tau. So if there is a point like this C which satisfies this particular ratio, then we can write this equation out. So essentially this part is tau and this part is tau plus 1 by tau. And once we write this equation here, we can simplify this equation and we get this particular quadratic equation. And if we solve the quadratic equation for a positive root, then we get tau is 1 plus root 5, whole thing divided by 2. And this is essentially the golden ratio. And as you can see here, because of the presence of root 5, this is not going to be a rational number. So it's going to be continuing on, and if we truncate it to 8 decimal places, we get 1.618033999. Now, interestingly, the Fibonacci sequence also comes across if we are looking at a golden ratio. So there is a relationship between the Fibonacci sequence and the golden ratio. So here you see the Fibonacci sequence, which is defined as Fn equals Fn minus 1 plus Fn minus 2, where n goes all the way 2, 3, 4 and continues like that. And F0 is defined as 1 and F1 is defined as 1. Now the Fibonacci sequence, if you use this particular definition here, would be F0 would be 1, F1 would be 1, then the next one F2 would be 2, because all you are doing is you add the last two numbers. Then you add 2 plus 1, you get 3, you add 2 plus 3, you get 5, you add 3 plus 5, you get 8, and so on. So this particular sequence keeps going on like this. And an interesting property of this sequence is that if you take the limit of Fn by Fn minus 1, then this limit tends to root 5 plus 1 by 2 or 1.618, which is also the golden ratio. And also the reciprocal of this golden ratio would then be Fn minus 1 by Fn. So it would be 2 by root 5 plus 1, and that becomes 0.618 as n keeps going on and on. So this is very interesting that this number comes across from various different type of mathematical phenomena, and therefore you can surmise that it is quite important as far as number theory is concerned. So now let's return back to our optimization problem. So what we do here is that we start from alpha is 0 and find the value of the function at the value delta. Alpha is delta, where delta is very small number. So this step is very similar to the previous method we have used. Now instead of taking it at 2 delta, 3 delta, 4 delta and so on, we start moving by putting in this 1.618 delta in the step size. So we add 1.618 delta in the step size and find the functions at following points and compare them. So for example, q is 0, we have delta, q is 1, we have delta plus 1.618 delta, so that is 2.618 delta. And then we start writing this out in a summation form, because this is going to bring out a certain pattern to this particular number. Similarly, q is 2, we get alpha 2 is 2.61 delta, which was here, and we add this to 1.618 into 1.618 delta. So this is the R delta which I was talking about previously. So you are accelerating forward rather than uniformly moving forward. And so now you have this 5.236 delta here, and all these are nicely represented in the summation form. So if you expand this out, you can see that, for example, let's try with this. If j is 0, you get the first term, and if j is 1, then you get the second term. And similarly, you keep going on and on. Now, the interesting part about this summation is that you can write the general term q, and the general term q would be j is 0 to q delta 1.618 to the power j, and this general term would hold for q is 0, 1, 2, 3, 4, 5, 6 and so on. So if you now look at the golden section method, what happens is that the intervals you have are becoming progressively larger. So you are going from delta 2.168 delta, 5.236 delta, 9.4718 delta and so on. While in the previous method we were moving forward at a constant velocity. So we had delta, 2 delta, 3 delta, 4 delta and so on. So therefore you can immediately realize that the golden section will bracket the minimum point in a more efficient manner and would take less number of steps to actually bracket that minimum point. But you see, the negative side is that the interval of uncertainty you will get in the first shot is likely to be larger than that obtained by the equal interval search. So for example, if my minima lies between 3 delta and 4 delta, this is going to be a smaller interval than if it lies between 5.236 delta and 9.4718 delta. So again, let us look at it graphically. So here is the f alpha function, and our one-dimensional function is like this. And we started here delta, 2.618 delta, 5.236 delta, and so on. And maybe we bracketed the minimum between these 2 points. So the function value kept decreasing all these points, and then it has reversed its direction here. So this is essentially how the golden section method will bracket the minimum point. And your alpha star lies somewhere in this particular interval. So now let us look at this bracketing of the interval more closely. Let us assume that the function at alpha q minus 1 is smaller than at q minus 2 and alpha q. That means if we look at this function here, we can clearly see this particular thing hold, that the function value at q minus 1 here is less than that at q minus 2. So this is clear. And also the function value at q minus 1 here is less than the value at q. So that also holds here. So when these two relations hold, then essentially your function has gone down and gone up, and you have successfully bracketed the minimum point between q minus 2 and q. So once you have done that, the interval bounds can be defined as follows. So we see that the alpha subscript u would be alpha subscript q, and from our previous derivation that would be the summation j is 0 to q delta 1.618 to the power j. Similarly, the lower bound would be the q minus second term, and this would be j is 0 to q minus 2, same expression as before here. So this is a general expression at any point q or q minus 2. So now the I value would be alpha u minus alpha L. And now if we look at this I value here, we can write down this expression from the previous slide, and then we can extract two terms from here. So we can extract the qth term, which will be delta this to the power q plus delta this to the power q minus 1, and the remaining terms will be the j's 0 to q minus 2 term, and those terms would all cancel out. So we are only left with these two terms. So now we can further simplify this by bringing out delta 1.618 q minus 1, and so we get 1 plus 6, 1 plus 1 plus 6, 1.618, and therefore I comes out to be this particular expression, which is a function of q and delta. Now here you can see that as q would be larger, I would increase in width. So this is what I was saying about the intervals becoming progressively larger as you go forward in the x domain or alpha domain. And the second fact is that this interval has now been bracketed to this level, and also of course it would depend on the delta value you have selected. If delta is small, this interval is going to be small, and so now that you have bracketed it, you can further reduce it by doing the same procedure more and more times. So again, this fits in very well with computer programming. So let us now look at how this particular golden ratio comes about in the context of this optimization problem. So let's start with this point alpha L and alpha U, and we have found 2 points alpha A and alpha B inside this particular interval located at a distance tau I from each end. So you will see that between alpha L and alpha B the distance is tau I, and same here between these two the distance is tau I. Okay, and therefore since the whole distance is I, this is going to be 1 minus tau I, this is going to be 1 minus tau I. And let us say we examine the values of this function at alpha A, alpha B, and based on these values we have shortened this value here. Now how we do that we will discuss soon. So by comparing the values of alpha L and alpha U, the left side or the right side of this interval will get discarded. That is the smaller interval. So there are two possible scenarios here. If the value at A is greater than B, then A and U is the new interval. And if A is less than B, then LB is the new interval. So we will assume for our calculation that right side gets discarded. So alpha L, alpha B are the new lower and higher bounds on the minimum. Now to see this graphically, you can see this kind of curve here. Now here f alpha A is less than f alpha B, which you can see here. So this function is lower than this function. So essentially you keep this interval here and drop this part. Now here in this case f alpha A is greater than f alpha B. So essentially you keep this interval here and you drop this interval here. So basically based on that philosophy, let us say we retain this part of the interval between alpha L and alpha B. And now I will try to figure out how to get the golden ratio. So let's look at the geometry of these two different line segments. So you can straight away see that this I superscript 1, which is the reduced line segment, is going to be equal to tau I, because tau I is this length here. So this is coming from geometry. Now you also see that tau I1, which is this distance here, is going to be the same as 1 minus tau I here. So you get this equation here, and in this equation you put I1 from this equation here, and therefore you get tau into tau I is 1 minus tau I. You solve this quadratic which comes out from this equation, and you get that tau is this value. To reduce it, you multiply top and bottom here, if you remember the philosophy of surds in mathematics. So this comes out to this form, and then essentially you get 0.618 here. So R comes out to 0.618, tau comes out to 0.618. So essentially then these lengths are all going to be, this is going to be 0.618 of I, this is going to be 0.618 of I minus, and similarly this is going to be 1 minus 0.618 of I, and so on. So the positive root of the quadratic equation we saw in the previous slide is the one with physical significance and is the reciprocal of the golden ratio. Thus the 2 points alpha A and alpha B are located at 0.618 and 0.382i from each end of this interval. So this is how essentially the golden ratio or the reciprocal of the golden ratio comes out in this problem, and that's why this is sometimes known as the golden section method or golden search method, and such nomenclature is used. So now this problem has become clear, so we can propose the algorithm which you can implement on a computer, or you can do problems by hand. You can see in the book there are some solved examples for this problem. So let's start this problem. For a small step size delta, let q be the smallest integer which satisfies this fact. So essentially this means that you have bracketed the minimum point, where alpha q is given by this general expression. Now the upper and lower bounds on alpha star, which is the estimated minimum point, are these two. And now what we do, we create this alpha A and we create this alpha B lying within the set here, or the set of points here, alpha U and alpha L. And these points we saw are coming from that partitioning of the line segment. And then you calculate f alpha A, f alpha B at these points, and you compare these 2 points and then go to the next step. Now the next step involves something which we have already discussed before, that if the function at alpha A is less than alpha B, then the interval essentially becomes between alpha L and alpha B. And then what you do, you replace this L star by L, U by B, and B by A. So essentially you are truncating the interval by declaring this as the lower bound, you can see here, this as the higher bound, you can see here, and one more of those points is captured in between. Now you can compute f of alpha A1 here, where this value is there, and then go to step 6. Similarly, if the function value is reversed here, f of alpha is greater than f of alpha b, then your minima lies between alpha a and alpha u. And therefore you set alpha L as alpha u, that's this value, you set alpha u as alpha u, that's this value, and then this alpha a1 becomes alpha b, compute the function value at that point, and then you go further. So once this interval is less than some small number epsilon, then you can calculate the minimum value at that particular point by taking the midpoint here, and then you can stop. Now if this has not happened, then you delete this script 1 on all these alpha values and then proceed back to step 3 and continue the search further. So you can see that this kind of method does not use derivatives, and it will probably require less function calculation than the equal interval search. Now function evaluations take an enormous amount of computer time for many problems. So very often we don't have simple functions out there. We may have complicated functions coming out from some computer code or simulation involving maybe solution of partial differential equations. And therefore the function calculation is very important, and therefore there is always the search for methods which are more efficient and which require lesser number of function calculation. So again, today we covered the golden section method, and I hope you understood this method, and maybe you can check out the book and look at some of the solved examples there and try to write a program in Python or C or whatever your preferred language is, maybe Julia or Fortran, to do this problem and to experiment with various different problems and test functions. So thank you very much for listening to this lecture 8, and I will come back to you with lecture 9 in the next video.